Every single time you click a link, fire off an email, or stream a video, there's this incredible invisible journey happening in the background. A message is literally racing from your computer, zipping across a global network to another machine, and coming all the way back, all in the blink of an eye. So in this explainer, we're going to pull back the curtain and make that invisible journey totally visible. We're going to trace the path step by step to see how it all works. So here's our game plan. We'll start with the big question. Then we'll look at the system of layers that makes it all possible. We'll check out the internet's actual blueprint, see how a message gets all packaged up, understand the rules of the road, and finally, watch how two computers make that final connection.
All right, let's just start at the very beginning. Forget all the complexity for a second. Just picture two machines. It could be your laptop right here and a server halfway across the world. And they need to have a conversation.
I mean, it really all boils down to this one fundamental question. How in the world does one box of electronics talk to another box of electronics reliably? What's the secret sauce? Okay, so on one side, you've got your computer. We call that the client. You type in a website, you hit enter, and on the other side, you've got this powerful server that's holding the web page you want. The big challenge is getting your request all the way from the client to the server, and then getting the server's response back to you through this massive tangled web we call the internet. So, the answer to this super complex problem isn't some single magical thing. Nope. It's actually a beautifully organized system of layers. You can think of it like the official travel guide for our data, making sure it never, ever gets lost. And this, right here, is the classic theoretical framework for that guide, the OSI model. The main idea behind it is simple, but it's absolutely brilliant. Divide and conquer. Instead of trying to tackle one massive, impossible task, network communication is broken down into 7 smaller, much more manageable jobs, or layers. Each layer has a very specific duty, and it only talks to the layers directly above and below it. So let's just follow the data as it makes its way down this ladder. It starts right at the top, in the application layer. That's simply the program you're using, like your web browser. From there, it gets passed down through layers that get it ready for the journey, make sure it's going to be delivered reliably, and figure out the best route to take. It finally gets all the way to the bottom, to the layers that handle the real nuts and bolts, turning your request into electrical signals or light pulses that get sent over the physical network. Now that 7-layer OSI model is perfect for a textbook. It's theory. But in the real world, the internet we use every day, it runs on a more streamlined, more practical version. So let's see what that actually looks like. This is the Internet Protocol Stack, but you've probably heard it called the TCP/IP model. It kind of collapses some of those OSI layers and gives us the 5 that really power today's internet. And you'll definitely recognize some of these names, right? The application layer uses protocols like HTTP for websites. The transport layer uses TCP for those rock-solid connections. And the network layer uses IP, which, of course, gives us the famous IP address. And here's a pretty cool little detail. As our data travels down through these layers on its way out, it actually gets a new name at each step. It starts as a message, then becomes a segment, then a datagram, and finally a frame. Why? Well, because each name tells you what kind of instructions it's carrying, which really helps network engineers figure out what's going on if something goes wrong. So we have all these layers, but how do they actually work together to get our data ready for its big trip? The best way to think about it is like you're mailing a letter. This visualizes a process called encapsulation. Our original message gets placed inside a digital envelope by the first layer. Then that whole envelope gets put inside another one by the next layer down, and so on. Each of these envelopes, which we call a header, has instructions that are specific to that layer's job. It's pretty amazing. Each layer just does its one job without needing to know what the other layers are up to. Let's break that down with our mailing analogy. At the application layer, you create your message. Hey, get me this web page. The transport layer adds its header with port numbers. That's like addressing the letter to a specific person inside a giant office building. Then the network layer adds the IP header. That's the main street address of the building itself. And finally, the data link layer adds instructions for just the very next step, like telling the local mail courier which specific truck to put it on. This whole system is pretty incredible. But it only works if every single computer and router on the entire internet agrees on what those envelopes look like and how to read them. They all have to be on the same page. They need a shared set of rules. And that's exactly where protocols come in. A protocol is simply the official rulebook. It defines everything: the exact format of a message, the order that messages are allowed to be sent, and exactly what to do when a message arrives. It's the shared language of the internet.
To make this crystal clear, just think about how we talk to each other. We have protocols too. You say hi, and I say hi back. You ask a question, and I give you an answer. Well, network protocols are literally the same thing, just for machines. A TCP connection request is just a computer's way of saying hi, and a GET request is its polite way of asking, "Excuse me, could I please have that web page?"
The thing is, the internet is kind of a chaotic place. Data can get lost, it can get corrupted, packets can show up in the totally wrong order. But the beauty of a really robust protocol like TCP, the Transmission Control Protocol, is that it's designed for this chaos. It automatically checks for errors, it re-requests any lost data, and it puts everything back in the right order, making sure you get a reliable, solid connection.
All right, so our message is wrapped up. The rules are all set, and we have a plan for dealing with any problems. Now let's look at the final, most critical step, how the client and the server actually start their conversation. The handshake.
This all happens through something called a socket, which is basically a doorway for communication. And programmers use these simple commands you see here to control that doorway. The server will create a socket, bind it to an address, and then it will listen, waiting for a knock on the door. The client, on the other hand, will create its own socket and use the connect command to do the knocking.
And this flowchart shows that interaction perfectly. It's really like a choreographed dance. You see the server on the left? It gets itself ready by creating a socket and setting itself to listen. And then it just waits. Meanwhile, the client on the right kicks things off with a connect. And once the server accepts that connection, boom, they can start that back and forth of sending and receiving data until one of them finally decides to close the connection.
Here's just another way to look at that same dance, but this time we're focusing on one critical moment, the synchronization point. This is the handshake. It's that instant when the server, which was just waiting patiently, finally accepts the client's connect request. At that exact moment, they are in sync, the connection is officially made, and the real conversation can finally begin. So there you have it. From a simple question to this complex system of layers, encapsulation, and protocols, that's the invisible journey of a single message. A journey that happens trillions of times every single day, powering our entire modern world. Understanding it doesn't just demystify the internet, it really shows you the foundation that everything else is built on. Which leaves just one question: what will you build with it?